This lecture will be about an example where I will go through some details of how the various computations are done. And this example is called the hyperbolic disk. It's a very nice example. Where I can show you some nice pictures at the end. We work with coordinates xi, and we have two coordinates kappa and phi, and the line element ds squared equals d kappa squared plus sine hyperbolic squared kappa d phi squared. And what we want to do, we want to find the Riemann curvature tensor. Remember that in 2 dimensions the Riemann curvature tensor has only one independent component. So what we need to do is find R12, 1, 2. If we can do this, then we are done. So how do we find the Riemann curvature for given line element? So start with, I believe the most efficient way is to use the Lagrangian approach to find all the non-vanishing Christoffel symbol components. So this is our Lagrangian. We recall that our Euler-Lagrange equations are d over d lambda dl dx dot I equals dl dxi when I say is 1. We are talking about the coordinate kappa. So we begin with the kappa equation. Looking here at the left-hand side, we have d over d lambda of, this is a simple function in terms of kappa squared, of kappa dot. So we get here simply 2 kappa dot. On the right-hand side, we need dl over d kappa. We need to differentiate this with respect to kappa. So we get 2 sine hyperbolic kappa cos hyperbolic kappa phi dot squared. The 2 cancels on both sides, and therefore our full equation is kappa double dot minus sine hyperbolic kappa cos hyperbolic kappa phi dot squared equals to 0, which we need to compare with x double dot 1 plus gamma 1 ij x dot I x dot j equals to 0, which immediately implies that gamma 1, 2, 2 equals minus sine hyperbolic kappa cos hyperbolic kappa, and all the other components that have a 1 on the top vanish identically. This means gamma 1, 1, 1 equals gamma 1, 2, 1. By symmetry, this is 1, 2, 1. And all these components are 0. Next, we look at the I equals 2 component, which means phi d over d lambda dl over d phi dot gives us sine hyperbolic squared kappa, which we don't touch, and then 2 phi dot. On the right hand side, we see that L is not a function of phi explicitly, so therefore we get a 0 here. We now need the product rule and the chain rule to differentiate this. As before, we cancel the 2. It begins with phi double dot sine hyperbolic squared chi plus phi dot, and now we need to differentiate sine hyperbolic squared kappa with respect to lambda. This gives 2 sine hyperbolic kappa cos hyperbolic kappa times kappa dot equals to 0. So this is the chain rule applied twice because we have sine hyperbolic squared of kappa, which is a function of lambda. So we have two outer functions, the square and then the sine hyperbolic of kappa of t. Hence we get all these terms out. And this is also equivalent to dividing by sine hyperbolic squared phi double dot plus 2. There are two sine hyperbolics here. There's one here, which means this becomes cotangent hyperbolic of kappa phi dot kappa dot equals to 0, which we now have to compare with the second geodesic equation. This means x dot dot 2 plus gamma 2 ij x dot I x dot j equals to 0. These are the mixed components, so this corresponds to the index values I equals 1 and j equals 2, or I equals 2 and j equals 1. Remember that the mixed components are counted twice because this is an honest sum over all index combinations, which means the only non-vanishing component is 2, 1, 2, which is cotangent hyperbolic kappa, while the other components are all 0. 2, 1, 1 equals 2, 2, 2 equals 0. This means we only have two non-vanishing Christoffel symbol components, not double counting this one. To find the Riemann curvature tensor, we now use the explicit formula. The explicit formula for R1, 2, 1, 2 is, recall that in 2 dimensions the Riemann curvature tensor has only one independent component. The 1, 2, 1, 2 component is this component. The 1, 2, 2, 1 component is also that component, just differs by the previous one, possibly by a minus sign. And therefore we can choose any of those. So provided we have the index combination 1, 2, 1, 2, we are fine. I'm having here an upper index because in the previous lectures our explicit definition of the Riemann curvature tensor always had an upper index at the end. So if you look into your previous lectures, where this was something like A, B, C, D, all we have to do is substitute in the corresponding values. What we get here is 2, 1, 1, minus 1, 2, 2, 1, plus gamma 2, 2s, gamma s 1, 1, minus 2, 1 s gamma s 2, 1. Remember, there is the summation over s still taking place. Let us have a look at our non-vanishing Christoffel symbol components. These are clearly, as we can see here and here, only functions of kappa. Kappa being, from up here, our first coordinate, which means d2 stands for d over d phi. However, none of the Christoffel symbol components are functions of phi. So this object is identically 0. Next, we have a look at this object here, gamma S11. Gamma 211 is 0, and from up here, gamma 111 is 0. Gamma 111 is 0, and gamma 211 is 0, which implies that gamma S11 is 0 for all index values of S, because S only takes values 1 and 2. Taking those two results into account, this simplifies. So that term is 0, which means we have partial 1 gamma 221. These two terms are 0. So we have here gamma 21s and gamma S21. Only one summation left over. We can now write this out explicitly. Minus partial 1 gamma 2 and then 2, 1 minus gamma. The summation is over both index values 1 and 2. This means 2, 1, 1, 1, 2, 1 minus gamma 2, 1, 2, gamma 2, 2, 1. We've said here already that gamma 2, 1, 1 is 0. This term is 0. So we are left with d over d kappa. Gamma 2, 2, 1. This is 0. And so we have only left this term here. 2, 1, 2, gamma 2, 2, 1. No further simplifications can be made. And now we substitute in the answers for our Christoffel symbol components. 2, 2, 1, cotangent hyperbolic kappa, minus, is this the same component as here, cotangent hyperbolic kappa squared. If you can't quite remember how to differentiate this, d over d kappa, recall the definition, cosine hyperbolic kappa over sine hyperbolic kappa, cotangent hyperbolic kappa squared. And then here we can use the quotient rule. I'm just copying the result here. So R 1, 2, 1, 2, 1, 2, 1, 2. Here we have a minus sign, which we keep hold of. The quotient rule begins with differentiating the numerator, multiplying by the denominator, sine hyperbolic squared kappa. We subtract the derivative of the denominator times the numerator. cos hyperbolic squared kappa divided by the denominator squared. Sine hyperbolic squared kappa minus, again, it makes sense now because it is written in this form to make it again explicit what the definition here is. Cos hyperbolic squared kappa. That looks bad. Divided by sine hyperbolic squared kappa. Now we need our you are almost tempted to use here the hyperbolic identity, but it's actually better not to do this. Because if you look at this, you see that here is a minus, there's another minus, so we actually have plus cos hyperbolic squared minus cos hyperbolic squared. These cancel. And we are left with minus sine hyperbolic over sine hyperbolic. Both are squared, which means we end up with 1. So the answer is minus 1. However, given that this is so nice and simple, we will continue and also compute the Ricci tensor now. And you will see the Ricci tensor will be of very special form. So by the way, if you wanted to now compute R1212, you have to be a little bit careful with this. By definition, it is 2s, G2s, 1, 2, 1s. Because we want to get this index 2 down here. If we now look at this, the only non-trivial component from our metric is the 2, 2 component. 1, 2, 1, 2. And G22, we can write this out here. Gij is 1, 0, 0 sine hyperbolic squared kappa, which means G22 is sine hyperbolic squared times minus 1. So R1212 with all lower indices is minus sine hyperbolic squared kappa. So you see that raising and lowering indices actually changes quite dramatically, in a sense, the values that we are looking at. So one has to be quite careful making interpretations based on results that depend on tensor valued quantities. So here you are almost tempted to say, aha, the Riemann curvature tensor is constant, but clearly this statement depends on precisely which form of Riemann curvature tensor you're looking at. Next, as I said, we want to compute the Ricci tensor. Next, let us compute the Ricci tensor. By definition, the Ricci tensor is RAB, and I want to use the 2-4 conventions, A, S, B, S. And we know that in 2 dimensions, we have 3 independent components, R11, R12, which is the same as R21, and R22. So those are the 3 components we are potentially interested in. Let us begin with the R11 component. You put in explicit values here for A and B, 1s, 1s. S can take values 1 and 2. So if I do this nice and slow, it is 1, 1, 1, 1, plus 1, 2, 1, 2. This term is 0 because the Riemann curvature tensor is skew-symmetric in the first pair of indices. Therefore, R1, 1, two arbitrary indices, is the same as minus R1, 1, two indices, because you can swap the ones over, you pick up a minus sign, and something can only be minus itself if it is identically 0. Which means we have found that our R11 component is the same as the Riemann tensor component up here that we computed. Therefore, R11 is minus 1. Let us next compute R22, because R22 is ever so slightly trickier. Again, we begin with the formal definition. 2s, 2s. We sum s over the two index values 1 and 2. R2, 2, 2, 2. As before, this object here is 0. The question is now, what is R2121? How can we answer this? Well, it is best to look at this. So we have R1212 is the same as minus R2112, which is the same as plus 2121. We are interested in this object where the last index is up. We can, for instance, say R2121 on the top is G1S R212S, because this is the definition of an upper index. You raise it with the metric. This is R11 R2121 plus G12 R2122. R12 is 0 and R2122 is 0. This is 0 because if you swap those two indices, it's skew, hence it must be 0. Therefore, this is 0. So therefore, this component of the Riemann curvature tensor is G11. If we scroll up, we see that our line element is nicely diagonal. There's a 1 here, hence the inverse metric has a 1 there as well. Therefore, this is 1 times R2121, which is the same as 1212, because we swap the first pair and the second pair of indices around, which means we pick up a minus sign and then another minus sign. That means this is minus sine hyperbolic squared kappa. Minus sine hyperbolic squared kappa, which are our two non-vanishing components. This means R22 is minus sine hyperbolic squared kappa. R11 was 1. Let us check the R12 component. R12 is R1S2. to S R11 21 plus R1222, which is identically 0 because R, when the first two indices are the same, is 0 because it is skew in the first pair. It is skew in the second pair, hence the same index value gives you a 0. If we now collect our result, we have the one non-vanishing component of the Riemann curvature tensor, which is equivalent to 1, 2, 1, 2 equals minus sine hyperbolic squared kappa, and maybe slightly more interesting, the components of the Riemann tensor can be collected like this. I'm sorry, this is the Ricci tensor, of course. And if we compare this with the metric we denoted up here, you all of a sudden see that this is a very special geometry. Namely, the Ricci tensor is proportional to the metric. These are very special spaces. In this case, we are talking about a space of constant curvature, in particular a space of constant negative curvature. Because we know the Ricci tensor explicitly, we can also compute the Ricci scalar. And as the name suggests, this is a scalar, and scalars are invariant under coordinate transformations. Because the metric is diagonal and so is the Ricci tensor, this calculation is very straightforward. We are only interested in the 1, 1 and the 2, 2 components. Likewise, you could substitute in the previous result here. It doesn't matter which way we do this. The result in either, independently of how we do this, the answers are equals minus 2. This is a space of constant negative curvature. And spaces of constant curvature are quite interesting from a geometrical point of view, and therefore I will make a few comments on these spaces, only very short ones. It turns out spaces of constant curvature will appear again in the cosmology course next term. So for those of you who like this course and are maybe interested in cosmology, it turns out that the space-time that is used to describe cosmology and the universe we live in contains a part that is a space of constant curvature. I'm writing this down as notes. Spaces of constant negative curvature Ricci scalar less than 0. They're called hyperbolic spaces. If you want to visualize them, you can think about saddles. Spaces of constant positive curvature, you all know those very well, are spherical spaces, which means you can just think about spheres. And you know that all spheres are topologically equivalent. Only the radius distinguish two spheres, and that radius is then inversely related to its curvature, which means spaces of constant curvature fall into really only three distinct cases. The ones with negative curvature, which are like saddles, the ones with positive curvature, which are our spheres. Finally, luckily those are trivial, spaces with constant, I say constant to keep the sentence the same, so with constant zero curvature are flat spaces. One has to be slightly careful here, so the emphasis is here that the entire Riemann curvature tensor actually has to vanish identically. But that's a slight technicality. So if we're speaking of constant curvature spaces, we have those three. And I think it would be a nice idea to show you a visualization of one of these hyperbolic spaces that some of you might have seen before. There is an artist by the name Escher. Just writing this here. Name is Escher. And the picture I'm going to show you is called limit circle 3. As you might have heard recently, Roger Penrose was awarded a Nobel Prize for Physics. It turns out he was a maths undergraduate at UCL, which is quite nice. Given his mature age, none of us can take any credit for ever having taught him. However, he is a graduate of this department, which is very nice. And to the best of my knowledge, there was some correspondence between the Penrose family and the Escher family. So Escher was very interested in geometry and visualizing geometry. Especially he was interested in hyperbolic space. And he came up with this beautiful picture that you hopefully now see of the hyperbolic disk. And I'm able to draw on this a little bit. I think, yes, I am. You clearly see a disk here, and you see these fish that populate the disk. The boundary of this disk I can't write on here. The boundary I have to write small. The boundary here corresponds to infinity. Which means that all these fish that are depicted in the circle, they are actually all of the same size. It is just as they are going further and further away and approach infinity, they appear smaller and smaller. So you should visualize someone being near you, and as they walk away from you towards the horizon, they appear smaller and smaller. This is, in a sense, the horizon. What is quite interesting also from a geometrical point of view that this visualization of the hyperbolic disk, for which we just computed that it is a space of constant negative curvature, so this visualization also contains the geodesics. These lines here, so I'm ruining the picture ever so slightly, I apologize for that. This line here is a geodesic. And these geodesics are geometrically characterized by being segments of a circle that intersect the boundary of the hyperbolic disk at right angles. And one can explicitly compute them given the line element that I've given you. So with this one here, it is quite nice to see that. In this hyperbolic space, these white lines are the shortest curves between 2 points. I can remove this one. If you lived in the space, if you wanted to travel from here to here, you would follow the black curve. And likewise, if you wanted to travel from this point to that point, the shortest distance to travel is along the geodesic. It's not along the boundary. This is longer than that. And if you take a tape measure and measure this distance, you will say, well, this is shorter than that. That is correct. But you, of course, in order to do this honestly, you have to use the given line element and honestly compute the distance of a curve connecting 2 points. And it turns out that if you do this with the given line element of the lecture, that this distance is in fact shorter than that distance. You can find some other really nice pictures of Escher. They're all online available. And if you spend a little bit of time looking at them, they're incredibly interesting. He drew various impossible pictures where you have a river that flows downhill and then back up into itself, or you have an infinite staircase that seems to be going down and then up on itself. They're very nice pictures, but especially the limit circled one. So this one is limit circle 3. They are very nice visualizations of the hyperbolic disk. And that's why I like discussing the hyperbolic disk as an example, because there are these beautiful visualizations. And if you have lots of time on your hands and you're really inclined to do so, it is a highly non-trivial exercise to actually compute those geodesic equations to convince yourself that they are circles and that the circles are defined in such a way that the endpoints here intersect the limit circle at exactly right angles. This is not easy to do, but doable because you know the answer. So if you know the answer, it's not too hard. So I hope this was a slightly entertaining finish to this lecture. So all we did today was we computed the Riemann curvature tensor and the Ricci tensor and the Ricci scalar explicitly for the hyperbolic disk, which is given by this line element that I'm going to show you again. This is the line element we started with for the hyperbolic disk. And the purpose of this example was really to show you explicitly what to do. For me personally, it is most efficient to find the Christoffel symbol components using the Euler-Lagrange equations, which follow from the Lagrangian induced by the line element, shall we say. Then we use the explicit formula for the Riemann curvature tensor, which in 2 dimensions is nice because we have only one component to compute. In 3 dimensions, we would have 6 of those to find. In 4 dimensions, which is the number of dimensions for special and general relativity, we would have 20 of those to compute. At which point you start seeing that this can be quite messy and will take a long time to do. And then I showed you explicitly how to compute the Ricci tensor by looking at the contractions of the Riemann tensor. I strongly suggest you go away from this lecture, start with the given line element, and see if you can reproduce these results from scratch. And a little side result in passing is that the space I gave you is very special in the sense that the Ricci tensor is proportional to the metric tensor. This happens very rarely. So there are very few spaces that satisfy this. It's these three types of spaces, and no other space does ever satisfy that. So have a look at this and make sure that you can compute Christoffel symbol components and Riemann tensor components for a given line element. Thank you for today.